Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Continuity Lecture 3 and we'll be talking about Algebra of Continuity, Intermediate Value Theorem and Continuity of Composite Functions. So let us begin our lecture with the Algebra of Continuity, which is nothing but recap from limits. Remember that we studied one table where we had two functions fx and gx and both limits were existing at a point A, that was L and M, right? And we did some addition, subtraction, multiplication, division, taking modulus, multiplying constant, making them composite functions, and we saw certain outcomes over there. Same kind of outcomes, exactly same kind of outcomes are applicable over here as well. For example, if we take one example over here, if fx and gx are two functions and both limits are existing, then fx plus gx limit would also exist, right? We studied that over there. In this case, if fx is continuous at a point, if gx is continuous at a point, in that case the summation of those two functions would also be continuous. And not only here, this kind of table is going to be applicable in case of differentiability as well, right? Now we missed out one point over there, that was about composite function. We said that we'll continue that in continuity, right? We'll study that in continuity. So now let us try to understand that point. So we have two functions fx and gx, and both of their limits are existing equals to L, and limit x approaches a equals to m. Both these limits are existing, right? And now if we talk about the composite function, limit x approaches a f of gx, and we said that this was equals to f of limit x approaches a gx. Okay, now this seems pretty obvious that we have pushed this limit inside this function and these two are going to be equal, but it's not that obvious. There's one condition under which this is going to be true. If that condition is not met, this is not going to be true. Okay, so let's try to build a thought process for that condition. Now when we are saying x is approaching a, we can simply say that gx is approaching m, right? Limit of gx is m, but when we are saying that x is approaching a, gx is approaching m, it's not exactly m, it's approaching m, right? Because we are not taking the limit over here, limit is outside, right? So we can simply write this as limit gx approaching m f of gx. Now when gx is approaching m, we can write this function as f of m plus h, right? When gx is approaching m, we can write this as f of m plus h, right? Because again, it's approaching m, it's not exactly m, right? When we take the limit, then the thing is different. But when we say that gx is approaching m, we mean that this is f of m plus h. This value, this function, this becomes f of m plus h. Okay. Now let us look at the right hand side, that is this part. Over there, what we are saying, this is f of limit x approaches a gx. Limit x approaches a gx is nothing but m. We are saying that these two values are equal. Now remember the basics of continuity. These two are going to equal only when the function is continuous, right? This is approaching value, this is the function value. This is approaching value, this is the function value, and both of them are actually equal when the function is continuous. If the function is not continuous, in that case they won't be equal, because this value would fetch limit of this value would fetch limit value, right? And this value would fetch the function value. This value would fetch the limit value, and this value would fetch the function value. And if the function is not continuous at m, in that case this might not be equals to this limit. Okay, that might be the case. Or maybe f of m is not defined, f of m plus h is defined because it's approaching value, but it might be possible that f of m might not be defined. So if this function is continuous at m, only in that case we can write this equation. We can put that limit inside the function, right? It looks complicated as of now, but it's pretty obvious that if the function is continuous at m, in that case we can write this equation. Okay, so this was the point which we missed out back in limits, because it wouldn't have been possible to explain this kind of thing back in limits. Okay, and now let us talk about intermediate value theorem. If f is continuous on AB and fa is not equals to fb, then for any value c belongs to fa fb, there's at least one number x in AB for which fx equals to c, right? So there are so many terms over here. Let's try to understand them one by one. So this is a, this is b, this is f of a, this is f of b over here. Okay. Now this is the point over here and this is the point over here. Okay. Now it says that fa is not equals to fb. We have done that. Fa is not equals to fb over here. Fa is continuous on AB. Let's draw a continuous function like this one, let's say. Okay, this is a continuous function over here. Then for any value c belongs to fa fb, let's take a value c over here. Okay, let's choose a different marker. So we have this c value over here. There is at least one number x in AB for which this fx equals to c. So there has to exist one number between a and b for which this function value equals to c, right? So this function is over here. So basically for this particular point there should be one x value between a and b, right? For this graph it seems pretty obvious, right? And that might be a fluke. Let's try to build a different graph over here. Let's say a, b, f of a, f of b. This is our first point, this is our second point. Let's say I draw something of, say, this sort. Okay, this is also a function. Now let's take a point c over here. Let's choose a different marker. Let's say I am choosing a point c over here. Now if I extrapolate that in the function, I'll be getting 1, 2 and 3 points over here. 1 point over here, 1 point over here and 1 point over here. I'm getting 3 points, and that is also true. At least one number, right? So we are getting 3 points over here between a and b. Okay, now let's try to create some different kinds of graph. Let's say this is a, this is b, this is f a, this is fb. Okay, this is our first point, this is our second point, and this is, and let's say this is our function. Okay, sorry, my bad. Let's say this is our function. Okay, now again taking a point c over here, extrapolating over here, and again we are getting one point between a and b. Okay, x1. Now it is clear that if the function is continuous between a and b, and if we are taking a point c between f and fb, in that case we are going to get a point x1 between a and b for that particular value on the function. Okay, so you can try out with different kinds of graphs, but continuous graphs, you'll always get a point between a and b over here. Okay, and now let's look at the alternate version of intermediate value theorem, which says if f is continuous on a to b, fa not equals to fb, and fa dot fb is less than 0, basically one value is positive and one value is negative, then there exists one root, at least one root of fx in a to b, which is the same thing, but the language is little different over here. Let's say we have a point over here, b point over here. This is f of a and this is f of b. Okay, so f of a is here and f of b is here. If I draw a continuous function over here, then no matter how I draw, if the function is continuous, it's going to always cut at a point, at least at a point between a to b. That means we are going to have one root between a to b for this particular function, right? At least one root. Main thing is at least one root. It's the same thing as the previous theorem, but the language is a little different over here. Okay, that's the only difference. And now let's solve this example. Using intermediate value theorem, prove that there exists a number x such that this function equals to 2005. Now this is nothing but, this value is nothing but c value. This is nothing but fx. And now what we have to do, we have to prove that this function is continuous, right? Because if the function is not continuous, we cannot apply intermediate value theorem, right? And we have to find out the range fa and fb to apply the intermediate value theorem. Okay, so let's first prove the function is continuous or not. We know that this function is polynomial function, which is going to be continuous. We know that this is a modified version of rational functions with a trigonometric function inside there, right? So in case of rational functions, we see the denominator part. We can see that denominator is always positive, because sine square x can, in the worst case, can take the value equals to 0, right? It cannot go below that, right? So 1 plus sine square x is always positive. So this function is continuous, this function is continuous. With the, by using the algebra of continuity, we can say that if one function is continuous, if other function is also continuous, adding both of them would also create a function that is continuous, right? So we have proved that this function is going to be continuous because this is polynomial. This is a modified version of rational function, which is nothing but a trigonometric function, and there is no possibility that this denominator is going to be 0, right? Now once we have done that, we have to find a range over here. So the obvious first point is 0, f of 0, right? F of 0 is nothing but 0 plus 1 upon 1, that is 1 only, right? Now f of, let's say, 1 over here, In that case, that would come out to be 1 upon 1 plus 1 upon 1 plus sine 1. But this is less than 2005. We have to find out a number bigger than 2005, right? So let's say we find out f2. We'll be getting 2 raised power 2005 plus 1 upon 1 plus sine square 2. Okay. Now this number seems to be bigger than 2005 because we have this huge power over here. Okay. So what we have got is we have got two numbers, f of 0 and f of 2. F of 0 and f of 2. We have got a range encapsulating this number. We have proved that this function is continuous. So that means there exists a number x such that this value is going to be taken by this function fx. Okay. And now let's solve this question. So there is at least one root of fx equals to cos x minus x square in 0 to pi, true or false. So all we have to do in this question, we have to find out if the function is continuous or not. And we have been given the range and we have to see if f of 0 dot f of pi is less than 0 or not, right? Only in that case, we have a root between 0 to pi, okay? So the first thing is, we know that cos x is always continuous, right? And x square is a polynomial function which is also again always continuous. So addition, subtraction, multiplication, division of two continuous function is always continuous, right? Except for a particular division case. But in case of addition or subtraction, it's always going to be continuous in case the two functions are continuous. Okay. Now we have proved that fx is continuous. So let's find out f of 0. F of 0 is nothing but cos 0, that is 1, minus x square, that is 0 square. So 1. And if we talk about f of pi, we'll be getting cos pi, that is minus 1, minus pi square, that comes out to be minus of 1 plus pi square, right? Now we know that this is a negative term. This entire term is always negative. This is positive. So f of 0 dot f of pi is less than 0, right? When we have proved that, we have easily proved that with the help of alternate intermediate value theorem that we have at least one root between 0 to pi for this function. Okay. And now let's talk about certain thumb rules regarding identification of discontinuity. So the first point is functions in intervals should be checked at points where definition of function is changing. What do we mean by that? Let's say we have a piecewise function fx equals to x square for x less than 0 and x square plus 1 for x greater than equals to 0. So we have definition of function changing at x equals to 0. So at x equals to 0, we have to check the continuity of this function, right? So whenever we have this kind of piecewise function, we have to check all the points where function definition is changing, right? So that's the first thumb rule to identify points of discontinuity, right? Now the second point is polynomial, rational, trigonometric, exponential, log functions, IDF functions are always continuous in their domains. This is the main point over here. So let's say there's a point given in the question which is in the domain of these functions. You can simply ignore that point, because that is going to be continuous. You don't have to check for the continuity or discontinuity at that point, right? So just remember that these functions are always continuous in their domains. Okay. Now the third point is fractional part function and GIF function should be checked at all points where the function becomes integer, right? This we have discussed earlier as well. Let's say we have this GIF function and we have x square over here. So we have to check at 1, root 2, root 3, 4, root 5, root 6, all these points, because this x square is becoming integer at all these points. Same goes for the fractional x square, right? In that case also we have to check at all these points. So whenever this inside function is becoming integer, we have to check at that point, right? Let's say we have a complicated function over here. Let's say x square plus sine x plus cos x. Let's say we have this function inside GIF. So we have to see if this entire function is becoming integer at what points. So at all those points, we are going to check the continuity of this function. Okay. So these are just certain thumb rules, right, to make your life easier for checking the discontinuity points. And now let's look at this question. Function fx equals to 1 upon log mod x is discontinuous in R at. Okay, we are talking about all points, not just domain. We're talking about all points. Okay. So first thing that comes to my mind after looking at the function 1 upon log mod x is log mod x is in the denominator and that should not be 0. That is the first condition, right? Because it is in the denominator. Now second condition is we know that modulus x is always positive or equals to 0. But can we have something equals to 0 inside log? We cannot have, right? So modulus x should also not equals to 0. So these two conditions are sufficient enough to find out the discontinuity points. So for the first condition, x can be 1 or minus 1, right? Because for 1 and minus 1, modulus x would take 1 only, and that would make this log as 0. So these are the 2 points based on which this condition is being satisfied, and for this point x not equals to 0 simply, right? So we have 2 points from here and 1 point from here, 1, -1 and 0. So we have 3 points over here. And now let's talk about continuity of composite functions, which is the last topic of today's lecture. So we have fx equals to x plus 1 upon x minus 1 and gx equals to 1 upon x minus 2. So if we talk about f of gx over here, we're getting gx plus 1 upon gx minus 1, right? Now, before moving forward, let's understand what is the continuity of gx. Why? Because definition of f of gx is dependent on continuity of gx, right? If function of gx, if basically gx is not defined, in that case, f of gx won't be defined at that point, right? If gx is not defined at a particular point, f of gx also won't be defined. So definition of f of gx is dependent on gx. So let's first understand the continuity or discontinuity of gx. Okay. So for gx, this is the function that is 1 upon x minus 2. And we know that this is a rational function. Rational functions are discontinuous at all the points where denominator becomes 0, right? Rational functions are the functions which are not defined or discontinuous at all the points where denominator becomes 0. Denominator becoming 0 at x equals to 2. So this is the first point where the function is not continuous. Since gx is not continuous, f of gx is also not continuous because definition of f of gx is dependent on gx. Okay, so this is our first point. Now second point is, this is our composite function, and this is also a rational function because we are using two rational functions over here. Ultimately, we are going to get a rational function over here, right? In that case, this denominator should not be 0 for this function to be continuous. This composite function is this one, and this comes out to be rational function, and this denominator should not be 0 for this function to be continuous. So we have to check all the points where this function is 0, where this denominator is 0, so that we get the point of discontinuities. Okay, so gx equals to 1. Gx equals to 1, that means x equals to 3, right? That is 1 upon 3 minus 2, that would be 1. Gx equals to 1 means x equals to 3, right? So we have got also point x equals to 3 over here. So we have got 2 points, x equals to 2 and x equals to 3. So if you want to summarize this, what we did, we first checked the continuity of gx because definition of f of gx is dependent on gx. And then when we wrote f of gx, then we checked the continuity of f of gx individually. So we have got 2 points over here, that is x equals to 2 and x equals to 3. Okay. So this is how you have to check the continuity of composite functions. And with this, we end the continuity for PGDBA. So let's meet in the next lecture, that is differentiability lecture 1. And thanks for watching.